Okay, so we're here on Monday, October the 19th to talk about chemical reactions, okay, and chemical equations. We should first say what a chemical equation is. A chemical equation is a symbolic representation of a chemical reaction, right? It's a symbolic representation of a chemical reaction, okay? Now, remember that we decided a while back that a chemical reaction and a chemical change are synonymous with each other. Okay? And back in chapter 3, we called them chemical changes. Now we're going to call them chemical reactions. Okay, so a chemical equation is just a representation of a chemical reaction. Okay, and back when we were doing that laboratory, we identified 5 or 6 ways to identify a chemical change. Change in temperature, change in color, creation of a new solid, evolution of a gas, creation of a new smell, emission of light. Okay, these are all indicators that a chemical reaction or a chemical change has occurred. Although they're not always. We talked about boiling water, you create a new gas, but that is not a chemical change. That's a physical change. So changes of state were examples where we might see one of those, but it was a physical change rather than a chemical change or a chemical reaction. So the first thing that we want to talk about in our discussion of chemical equations is how to do what's called balancing chemical equations. So we're going to begin with a very, very simple one. A very, very simple chemical equation. Okay, so here we go. All right, now this is the combination of nitrogen gas with hydrogen gas to give us ammonia gas. All right, now when we say to balance this, what we want to do is have the same number of atoms of each element, the same on both the reactant side and the product side. So we can see this is not balanced. Here I have 2 nitrogens here, but only 1 here. We should say that a subscript multiplies what comes immediately before it. So immediately before this 2 is a nitrogen. So there's 2 nitrogens here. Okay? Here, if there's nothing written here, it's understood that there's a 1 there. So we have 1 nitrogen and 3 hydrogens. So the nitrogens are not balanced. 2 here and 1 here. Nor are the hydrogens balanced. There's 2 here and 3 here. Okay, so our task is to get the number of atoms of each element the same on the reactant side and the product side. Okay, now we're going to use what's called a brute force or a trial and error approach. Okay, there is a longer, much more sophisticated method for this sort of reaction. That will lead you, if you apply it properly, will get you to the right answer without error every single time. Okay, now, but that method is way over our needs for this introductory chemistry class. You want to see how to do that, take general chemistry. Okay, so that's the balancing of oxidation reduction reactions. And we'll talk more about reaction types. Hopefully we'll get there today. Okay, so the way I like to do this is I just write down reactants and products. And I write down the atom types and copy them the same on both sides. Reactants and products. Write them down, the atom types down, the same order on both sides. Then I'm going to write down how many of each element there are. So there's 2 nitrogens and 2 hydrogens. Here there's 1 nitrogen and 3 hydrogens. 1 nitrogen and 3 hydrogens. Okay, now, again, even though this is a trial and error approach, there are a number of little tricks or bits of advice to get you to the proper answer quickly. All right, and we have one of them in this problem right here. Okay, so here I see an even number of hydrogens and an odd number of hydrogens. An even number of hydrogens and an odd number. Okay, and this is it. If there's a very useful thing to do when you have a situation such as this, an odd number on one side and an even number on the other side. So what you want to do is ask, what's the lowest common multiple of 2 and 3? What is it?
One.
6.
What number, what's the smallest number that has 2 and 3 as factors?
6.
6. So I'm going to want to put 6 hydrogens on each side. 6 hydrogens on each side. Now, to do this, we cannot change subscripts. We cannot change subscripts. The only thing we can do is put numbers in front, because there's a nitrogen molecule, N2. All I can do is put a number, some number in front here, some number in front here, and some number in front here. That's the only thing I can do. The only thing I can do. If I change the subscript, I'm changing the chemical. I'm changing the chemical. Okay? So, again, the only thing I can do is put what are called coefficients in. Same as in your math class, right? Coefficients. So, we said that the, is that the right math term? The lowest common multiple? Okay? Or, again, another way to look at it, the smallest number has 2 and 3 as factors, is 6. So I can put a 3 here. That gives me 3 times 2 is 6 hydrogens, and I'm going to put a 2 here. Right? So how does this change? We got to make changes down here. 3 times 2 is 6 hydrogens. Over here, I'm going to cover up. I see 1 nitrogen. So we didn't just change the hydrogens here. We also changed the nitrogens. So a subscript multiplies what immediately is before it. A coefficient multiplies everything after it in that chemical. A coefficient multiplies everything after it in that chemical. Again, if you don't understand something, please speak up. So what I like to do is cover up the coefficient. I see 1 nitrogen times 2 is 2 nitrogen. I see 3 hydrogens times 2 is 6 hydrogens. 2, 6, 2, 6. We're done. We're done that fast. Okay, but you should always go back and check, because you can make mistakes down here. And you will make mistakes. All right, so it's always good to spend a few more. So now this is a trivial one, but some of them get quite a bit more complicated. Okay, just spend a few seconds to double check what you've done. 1 times 2 is 2 nitrogens, 2 times 1 is 2 nitrogens. 3 times 2 is 6 hydrogens, 2 times 3 is 6 hydrogens. Now we're done. We have checked it. We have checked it. Any questions here? Any questions? Okay.
No.
Now, I do want to talk a few more things about this. Okay. And we want to look at some items that are conserved. Okay. Some items that are conserved. But before we do that, I just want to mention, I want to digress here just for one moment and talk about this reaction. This is a very, very famous reaction. Oh my God, I forget this guy's name every time. It'll come to me. But this was a famous reaction that won a Nobel Prize for a German chemist around the time just before World War I. This is, I can't remember his name. Oh, geez. But anyway, at the beginning of World War I, Great Britain put a naval blockade around Germany, right? And because you use this, there's 3 steps in this chemical process to make nitrates. Nitrates are used to make gunpowder. So this is one of the steps. One of the steps. I think it's the first step, if I remember correctly. Let me see if I have it here. All right, anyway, so this is one of the first steps to make nitrates. You can make nitric acid, and then from nitric acid, I believe from this you can make nitric acid, and from nitric acid you can then make nitrates. And nitrates are used in gunpowder. So if you're going to fight a big war, Germany's about to fight a big war with England and France, you have to have a lot of gunpowder. Well, Great Britain put a naval blockade around Germany, and Germany was importing its nitrates from Argentina. Great Britain was the major naval power, and at the time, so they easily put a blockade around Germany. Germany can't import any nitrates, and lo and behold, pretty much the war is over before it even starts. But Germany has something in reserve. They have tremendous scientists, as did England at the time. So they put their scientists to work. This guy came up with this reaction. It's very difficult to get this reaction to work. Nitrogen is relatively inert gas. I mean, it's the major component of the Earth's atmosphere, right? It's a relatively inert gas. So you have to get this reaction to occur. You have to do it under very high pressure, very, very high temperature. And so this guy got this to work. He became famous. He won the Nobel Prize in chemistry for this reaction. I have his picture up in my classroom. I should have looked before I came here today. Let's see. Where's my synthesis reactions? Oh, I know I printed them out. Okay. Anyway, okay, here they are on top. Let's see if I have his name right here. So again, this was a very, very famous reaction during World War I. I don't have his name. Every year I forget this guy's name. Again, he was a very, very famous chemist. All right. Now that we have that aside, again, this was crucial during World War I, getting this reaction to work. Because once the Germans got this reaction to work, you get nitrogen out of the air. 78% of the atmosphere is nitrogen. Hydrogen gas, run electric current through water, and you have hydrogen gas bubble out. So essentially, you can make all the ammonia that you want. You can then make nitric acid, leading to nitrates, okay, which is a major component of gunpowder. All right, with that aside, let's take a look at what I want to discuss. What is conserved here? What is conserved? Okay, well, one thing that is conserved is atom type. Atom type. And by that, I mean we have the same number of atoms of each element on both sides. 2 nitrogens here, 2 nitrogens there, 6 hydrogens here, 6 hydrogens there. So atom type is conserved, right? The same number of atoms of each element on both sides. Okay, let's take a look at whether or not the number of protons are conserved. Well, let's see. Here I have 2 nitrogens, so that's 14 protons. Here, we'll just write 14. We know they're protons. Here I have 6 hydrogens, that's 6 protons. All right, we can think of this arrow as an equal sign. We've talked about this before when we discussed conservation of mass. Okay, so here, let's take a look there. There's 1 nitrogen, that's 7 protons, and 3 hydrogens is 3 more protons. So in 1 ammonia molecule, NH3, there's 10 protons. Times 2 is 20 protons. 14 plus 6 equals 20. So protons are conserved. Protons are conserved. All right? Now, let's take a look here. We talked about ions. I don't see any charges here. All of these chemical species are neutral. They are all neutral. If they're neutral, the number of electrons must equal the number of protons. And we saw protons are conserved. So electrons must be conserved. Electrons must be conserved. Okay? Now, we learned in chapter 3, what were the 2 big things in chapter 3 that we learned were conserved in every physical or chemical process? Anybody remember? The 2 big things that were conserved. What were the 2 big topics in chapter 3? Conservation of what?
Mass?
Just a minute ago. I heard somebody mumble something.
Mass?
Mass. Conservation of mass. and what else?
Energy.
Energy. Energy. All right, so these two are conserved in every chemical reaction. Every chemical reaction. Now, let's take a look here. If protons and electrons, if their numbers are conserved, right, they're the only things that are charged, that are electrically charged in atoms or molecules, are protons and electrons. If they are conserved, then electric charge must be conserved. Actually, I'm going to write that down on the bottom. Charge must be conserved. All right? Electric charge must be conserved. Now, I left something else here. Okay, now, we learned when we did isotopes that mass is equal to what? The mass of an isotope is equal to what? Of an atom. Anybody remember? Oh, come on, this wasn't that long ago. Protons plus what?
Neutrons?
Neutrons. Protons plus neutrons. Okay, so let's take a look here. If mass is conserved and protons are conserved, then the neutrons have to be conserved also. If this doesn't change and that doesn't change, this can't change either. So neutrons also are conserved. Neutrons also are conserved. So these 7 things, these 7 parameters are conserved in every single chemical reaction. Every single chemical reaction. Okay? Now, we can't prove here that energy is conserved, but we learned in chapter 3 that it's conserved in anything that happens. Energy is conserved. These other ones we can all prove just from what we did here. All right? We can prove that they're conserved. All right, now, and do we have any questions there? Any questions there? All right, I want to point out one thing here, that while atom type is conserved, the number of molecules is not. Here I have 1 molecule of nitrogen, 1 molecule of nitrogen, and 3 molecules of hydrogen equals 2 molecules of ammonia. That's not true. So the number of molecules is not always conserved. Sometimes it is, but most of the time it won't be. It does not have to be conserved. Right? The number of molecules or number of ions are not always conserved. Sometimes they are, sometimes they're not. But these things in red here are always conserved. No matter what reaction we're talking about, they are conserved. All right? So molecules, ions, not always conserved. Okay? Any questions or comments here? Any questions or comments? So again, we saw our first bit of advice. When you have an odd number and an even number, find the lowest common multiple and put coefficients in to get that number of atoms on both sides. All right, so I'm just going to do a bunch of these, balance a bunch of these. And we should look at reaction types also. Usually I do those separately, but I think I'm going to do them in combination with what we're doing here. All right, let's look at here. This. Okay, so here I'm going to write reactants and products, phosphorus and bromine, and phosphorus and bromine. Okay, now, here I have 4 phosphorus and 2 bromines. Here I have 1 phosphorus and 3 bromines. Okay, now, here we have a similar situation as in the last problem. I've got an even number of bromines here and an odd number there. An even number and an odd number. So this is going to be very similar to the last one. Okay, but we could do that. But I see if I'm going to put a 2 here, why not take care of the phosphorus first? I have 4 here and 1 there. Again, you can do these. You can. There's no set manner in which order of steps in which you use to balance the equation. We could do the even odd thing first. But here I'm going to do 4 phosphorus and 1 phosphorus. I'm going to take care of that first. So I'm going to put a 4 here. Right, that takes care of the phosphorus. So let's go ahead and do that. We got to change it down here. 1 phosphorus times 4 is 4. 3 bromines times 4 are 12 bromines. 12 bromines there. Right, so now the phosphorus are balanced. So now I'm going to take care of the bromines. Here I have 2 bromines. So what number times 2 equals 12? What number times 2 equals 12? So I just put a 6 there, and that gives me 12 bromines. 12 bromines. So as always, you go back and check. Okay, 1 times 4 is 4 phosphorus, 4 times 1 is 4 phosphorus. 6 times 2 is 12 bromines, 4 times 3 is 12 bromines. We're done. We're done. Okay, any questions here? Any questions? Okay.
Yeah. How do you
Somebody has a
how do
question?
you check it again?
Is there a question?
Yes, sir. It's how do you double check
You got to speak louder.
again?
I can't, wait, maybe I have to turn up my speakers.
I was
Yeah, I
just
have them
wondering.
down low. Okay, go ahead. I have my speakers down low.
Okay, how do you double check again?
You just go back up to your equation here. I have 1. My coefficient here is 1. If there's no coefficient, it's understood to be 1. 1 times 4 is 4 phosphorus. All right, so that's 4 on this side. Over here, I have 4 times 1 phosphorus is 4 phosphorus. All right, here I have, okay, my bromines. 6 times 2 bromines are 12 bromines. 4 times 3 is 12 bromines. Remember, a coefficient multiplies what comes immediately before it. Coefficient, or wait, sorry, did I say coefficient? Subscript. Subscript multiplies what comes immediately. Here, let's do it over here. Subscript multiplies what comes immediately before it. So that 3 only multiplies the bromine, not the phosphorus. There's an understood, I'll write it in red, there's an understood subscript of 1 on the phosphorus. All right, so in the chemical formula, every element has a subscript. There's one not explicitly shown, it's understood to be 1. It's understood to be 1. So a 3 bromines times 4. Now remember, coefficient multiplies everything after. So there's P1, Br3. This 4 is going to multiply everything. So 1 phosphorus times 4 is 4 phosphorus. 3 bromines times 4 are 12 bromines. 12 bromines. Does that clear up? Whoever asked that? Did that clear that up? Come on, somebody say something. All right, I'll move on. Nobody said anything. Now we should mention what kind of reaction this is. All right, like I said, I usually do that separately, but I'm going to combine the balancing with what type of reaction this is. This is what's called a synthesis reaction. Synthesis. And how do we spot a synthesis reaction? Actually, I want to use the same notation that our textbook does. And if I remember, because sometimes I use different ones, and I believe this is chapter 6 or 5. So we're kind of combining a number of different things out of the textbook here together. Again, I just want to make sure we're using the same notation. Okay, here we go. All right. So the general format of a synthesis reaction is A plus B gives me AB. All right, A plus B gives me AB. If you think about it, the word synthesis means to make, right? Synthetic fabrics like nylon, rayon, polyester. Okay, those are artificially made. All right, they're not natural. All right, so two things become one. It's very easy to spot a synthesis reaction. It only has one product. Very easy to spot a synthesis reaction. It only has one product. Okay? It's a dead giveaway that it's a synthesis reaction. It's a dead giveaway that it is a synthesis reaction. Okay? Any questions on this one? This is also another kind of reaction, but I'm not going to say it yet. We'll do it on the next one. Right? Any question or comment here? Any question or comment? Okay, the general format of a synthesis reaction, one product. All right, let's do another synthesis reaction here. Okay, this is going to be a nice, easy one here, but I'm going to use it to demonstrate this other type of reaction. All right, so we're combining sodium metal with chlorine gas to give us sodium chloride. All right, so just again, it's a nice, easy one. They get harder, and we'll progress to some harder ones. All right, so here I have sodium and chlorine. Copy them in the same order on both sides. Here I have but one sodium and two chlorines. Here I have one sodium and one chlorine. All right, one sodium and one chlorine. Now, okay, well, the sodiums are already balanced. The chlorines are not. So I have two chlorines here and one there. I got to have two over there. So I'm just going to put a 2 there. We'll put a 2 there. Cover up. One sodium times 2 is 2 sodiums. One chlorine times 2 is 2 chlorines. Okay, so now the chlorines are balanced. The sodiums are not. I have 1 on the reactant side and 2 on the product side. We can easily rectify that by putting a coefficient of 2 on the sodium. Here I have 2, 2. 2, 2. But again, I promise you, you're going to make mistakes down here on the bottom. So we go up and check. 2 times 1 is 2 sodiums. 2 times 1 is 2 sodiums. 1 times 2 is 2 chlorines. 2 times 1 is 2 chlorines. We're done. We're done. Okay? Now, any question or comment? Now, notice this is also a synthesis reaction. We have one product. We just have one product. Okay? Now, this is also what's called an oxidation reduction reaction. An oxidation reduction reaction. This is a very large class of chemical reactions. A very, very large class of chemical reactions. Right? It's enormous. Okay, the vast majority of chemical reactions are oxidation reduction. All right? Now, what happens during an oxidation reduction reaction? Electrons get transferred from one atom to another. Electrons get transferred from one atom to another. So we're going to use this little simple reaction to prove that that's occurring here, right? That is occurring here, right? So oxidation reduction. Quite often we'll just say redox. Chemists will just say redox. So if you hear me say redox, that's this, oxidation reduction, okay? And I mentioned to you that there's a systematic procedure for balancing. And that is the balancing of oxidation reduction reactions. Okay? And it's a very sophisticated method, but it works every time if you apply it properly. All right. So we want to prove that electrons are being transferred here. So here, what's the charge on this sodium atom here? What's the charge on the sodium atom?
+1,
No. No. 0. It's a pure element. It's a pure element. It's 0. How about on these chlorines? What's the charge on those chlorines?
Wouldn't it be -1, or is it still?
0. 0. Now, be careful here. What's the charge on that sodium? What kind of compound is that? Is that a molecular compound or an ionic compound? What kind of compound is that? Molecular or ionic? How do you spot an ionic compound? Anybody remember? It must have a what? It always begins with a what? Or at least most of the time. Begins with a
metal.
A metal. All right, an ionic compound must contain metal cations and non-metal anions. There's our metal cation, there's our non-metal anion. So what's the charge on sodium cation? What's the charge on sodium cation?
+1.
+1. You should have a periodic table there in front of you. What's the charge on chloride anion?
-1.
-1. So here, we have proven that this is an oxidation reduction reaction. Right? The sodium started out neutral, ended up as +1. That means it lost an electron. It lost an electron. The chlorine started out as neutral and ended up as -1. It gained an electron. So the sodium, so an electron has been transferred from the sodium to the chlorine. An electron has been transferred from the sodium to the chlorine. Okay, here we have 2 chlorines, and 2 sodiums. Each of the 2 sodiums has given up an electron to a chlorine atom. Right, and we end up with a sodium cation and a chloride anion. Right, so again, we can see here that an electron has been transferred. This is in fact an oxidation reduction reaction. Okay, so how do we spot an oxidation reduction reaction? Well, quite often you'll have to do that very sophisticated approach, but we're going to simplify it. We're going to take a simplified approach. All right, so how we're going to spot an oxidation reduction reaction is if the reaction contains a pure element. If the reaction contains a pure element, it must be an oxidation reduction reaction. If a reaction contains a pure element, it must be an oxidation reduction reaction. So let's look at a Venn diagram here. So here we have the universe of oxidation reduction reactions. All right, those that contain a pure element are like this, right? PE, pure element. There are many other oxidation reduction reactions that do not contain a pure element, but we are only going to be concerned with these ones. Okay, everybody clear on that? I don't want somebody coming back to me and saying, oh, what's that guy saying? There's plenty of oxidation reduction reactions that don't have pure elements. Yes, that's true. Yes, that's true. Okay, so but these out here are above the scope of what we're trying to do in this class. You want to know about these out here, take general chemistry. Okay, any question or comment here? So again, notice this is also a synthesis reaction. Right? This is also a synthesis reaction. One product makes it synthesis. Okay, pure element makes it oxidation reduction. Okay, any question or comment? Any question or comment? All right. Now, I'm never going to ask you to prove that a reaction by writing up here, but you should be able to do that. I mean, you know enough information to do that. All right, let's look at another reaction here. I have big databases of these things. Let's see here. Okay. So we're going to write down reactants and products. So here I have sodium and nitrogen. Sodium and nitrogen. Same order on both sides. Same order on both sides. So here I have 1 sodium and 3 nitrogens. Here I have 2 nitrogens and 1 sodium. All right. Now this clearly is not a synthesis reaction. All right. It's got 2 products. So what are we going to do? What are we going to do? Anybody? Sorry, I didn't. All I heard was that was pretty gargled. What are we going to do there?
Multiply the 3 and the 2 together.
Yes, very good. Okay, we have an odd number here and an even number there. The sodiums are already balanced. We have an odd number here, nitrogens on the reactant side, the even number on the product side. So the lowest common multiple of 3 and 2 is 6. So I'm going to want to make 6 nitrogens on both sides. So I'm going to put a 2 here. 2 times 3 is 6. All right, I'm going to put a 2 here and a 3 there. All right, so let's change our numbers down here. There's 1 sodium times 2 is 2 sodiums. 3 nitrogens times 2 is 6 nitrogens. All right, so that takes care of this. And over here, 2 nitrogens, and cover up here. 2 nitrogens times 3 is 6 nitrogens. And number of sodiums stay the same. The number of sodiums stay the same. So now I have 2 6 and 1 6. All I got to do is put a 2 in front of the sodium, and I'm done. 2 6, 2 6. 2 6, 2 6. As always, we're going to go back and check. 1 sodium times 2 is 2 sodiums. 1 sodium times 2 is 2 sodiums. 3 nitrogens times 2 is 6 nitrogens. 2 nitrogens times 3 is 6 nitrogens. Okay? Anybody have any idea what this reaction is? I believe this is what happens in an airbag in a car. Right? Sodium azide is in the airbag. So when there's a shock, what's called decomposition happens. This is, of course, a gas. So we know gases rapidly expand, right? They rapidly expand. I believe this is an exothermic reaction also. So this is a hot gas. So it expands very, very fast. It fills the airbag immediately. Right? This is also a quite toxic compound. It will eat metal pipes, but it's also a bactericide. So in bacteria, when I used to work in biology lab, all the chemicals I made, we would put a very small concentration of this compound, sodium azide, into it because it would kill any bacteria. But you got to be careful about dumping it down the drain because it will eat away at the pipes. Okay, so that's this reaction. Now, we see that it's an oxidation reduction reaction, pure element there, pure element there. This is clearly an oxidation reduction reaction. Okay, now it's also another type of reaction, right? We see that it's let me erase this down on the bottom here. This is also another type of reaction. We see it's the opposite or the inverse of a synthesis reaction. It's the opposite of a synthesis reaction. Here, instead of having 1 product, we have 1 reactant. Anybody have any idea what this might be called? We have one thing breaking apart into 2. When you die, what's going to happen to your body? It's going to...
Oh, is it decomposition?
It's going to decompose. So this is called a decomposition reaction. A decomposition reaction. So let's write that down. Decomposition. And again, it's the inverse of a synthesis reaction. So what's the general format of a decomposition reaction? AB goes to A plus B. 1 reactant. So just like a synthesis reaction was extremely easy to spot one product. Okay, a decomposition reaction is extremely easy to spot one reactant. One reactant. And again, just from the name of these types of reactions, you should be able to figure out what it is. Decomposition means something breaks apart. That's exactly what's happening here. Sodium azide is breaking apart into nitrogen gas and sodium metal, right? And this, we could write this in the reverse direction and it would become a synthesis reaction. Okay, so one reactant is always going to be a decomposition reaction. Okay, but again, this is also, a reaction can be more than one type. So this is also an oxidation reduction because it has pure elements in it. Pure elements. Okay, any question or comment? Any question or comment? All right. Let's look at another type here. Rather than do this off the top of my head, have these databases, may as well use them. These are L's, that's aluminum. Okay, we'll give you a moment to copy that down. We're working out of chapter 7 here. Although we're combining some things from, I can't remember what other chapter it is, an earlier chapter. Okay. We're going to write down reactant and product. So here I have aluminum and chlorine and copper. Same order on both sides. Same order on both sides. I don't want this to look like a 1. All right, so here I have 1 aluminum. Let's write the numbers in a different color. Tell me if you guys can't see this red. Can you see that?
Yeah, we can see it.
Okay, and 3 chlorines and 1 copper. Here I have 1 aluminum, 2 chlorines, and 1 copper. So what are we going to do? Now, let me just give you a bit of advice here. All right? You never begin with a pure element unless you have no other choice. So here I have copper and aluminum, both appear as pure elements. Do not ever begin with a pure element unless you have absolutely no other choice. Okay, do we have another choice here? Well, here I clearly don't want to begin with them anyway. The aluminum's already balanced, 1 and 1, and the copper is already balanced. But again, if they weren't, you never begin with a pure element unless you have no other choice. So the only thing that's not balanced is the chlorine. 3 and 2, there's our lowest common multiple again. All right, so I'm going to make 6 chlorines on each side. How am I going to do that? I'm going to put a coefficient of 2 here and a coefficient of 3 there. All right, and then we're going to fix our numbers here. So 1 aluminum, let's cover up here. 1 aluminum times 2 is 2 aluminums. All right, 3 chlorines times 2 is 6 chlorines. And the copper stays the same. Copper stays the same. Over here, I have 1 copper times 3 gives me 3 coppers. 2 chlorines times 3 gives me 6 chlorines. And 1 aluminum doesn't change. All right. Now you can see why you don't mess with pure elements until the end. Why you don't mess with pure elements until the end. Very easy. I have 2 aluminums here and 1 aluminum there. All I got to do is put a 2 here. Takes care of the aluminum. Here I have 3 coppers. Here I have 1 copper. Very easy. Just put a 3 there. 263, 263. All right. So we're going to go back and check. We're going to go back and check. All right. 1 aluminum times 2 is 2 aluminums. 2 aluminums. 3 chlorines times 2 is 6 chlorines. 2 chlorines times 3 is 6 chlorines. 3 coppers, 3 coppers. We're done. We're done. Any question or comment? So what kind of reaction is this? Let's see, we've done synthesis. Is it a synthesis reaction?
Yes.
That's a synthesis reaction. How do you spot a synthesis reaction? How do you spot a synthesis reaction? Anybody, come on, somebody got to know.
A plus B equals AB.
No, that's not how you spot a synthesis reaction.
It only has one product?
It only has 1 product. Is this a synthesis reaction?
No.
No. All right, the other type we spotted was decomposition. How do you spot a decomposition?
If it contains a pure element.
No. How
If
do you
there's 2
spot
products.
decomposition? Say it?
If there's 2 products.
No. Come on, I just said this like 3 minutes ago. How do you spot a decomposition? 1 reactant. Remember, as AB goes to A plus B, 1 reactant. Is this a decomposition reaction?
No.
No, it's not. It's got 2 reactants. Remember, there's our arrow. Let's make this arrow stand out a little better. I'm putting it in red. All right, there's our arrow. It has 2 reactants. It cannot be decomposition. It has 2 products. It cannot be synthesis. Now, the third type of reaction we saw was oxidation reduction. Is this oxidation reduction? How do you spot an oxidation reduction reaction? How do we spot oxidation reduction?
Based off of charges.
No. Come on, I told you a very quick way to spot an oxidation reduction reaction. Somebody said it earlier, but for the wrong type of reaction.
If it contains a pure element,
Right, if it contains a pure element. Is this an oxidation reduction reaction?
Yes.
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 There's pure copper. It's copper by itself. There's aluminum by itself. I have 2 different pure elements. I only see 1 element there. I only see 1 element there. This is a compound. This is a compound. There's 2 elements there. That's a compound. Okay, that's a compound. So this is an oxidation reduction. Okay, now it's also another type of reaction that we haven't seen yet. So let's take a look at what's going on here. Okay, the aluminum and the copper are trading places. The aluminum and the copper have traded places, right? Here, the copper is by itself, the aluminum is with the chlorine. Over here, the aluminum is by itself and the copper is with the chlorine. So this is what's called a single displacement or single substitution. Let's see what our book calls it. Some books call it displacement, some call it substitution. Our book calls it displacement. Single displacement. So the copper is displacing the aluminum. Okay, so what is the general format for a single displacement? Okay,
AB. Oh, are you asking us or are you just going to do it?
I'll do it.
Okay.
I'll tell you what, for this one, I'm going to use a different notation than our book does. I'm going to use a different, I like this notation better. And I'll say why in a moment. Okay? So I use the lower letters in the alphabet for the cation, and then the X, Y, Z for the anion. All right, so the X is the chlorine, the A is the aluminum, the B is the copper. All right, I think it's a little easier to spot that. And notice here, the aluminum, the A and the B trade places. So here, the metal cation is what's being displaced. The metal cation is being displaced. Okay? Now, again, you should be able to draw these little arcs like this. All right? But what's a good way to spot a single displacement? You'll never remember this, but, okay, it contains a pure element and an ionic compound on both sides. A pure element and an ionic compound on both sides. All right? That's an easy way to spot a single displacement reaction. An easy way to spot a single displacement reaction. It's got a pure element and an ionic compound. A pure element and an ionic compound on both sides. Right? But you ain't going to remember that. You should be able to just draw these little loops, okay, to help guide you. Okay? And we said this was also oxidation reduction because it's got pure element. It's got copper and aluminum as pure elements. Right? So single displacement. Single displacement. Any question on this single displacement? Any question on this single displacement? Now, again, we said here the cation, the metal cation is being displaced. The copper is displacing the aluminum. Let's look at this next one where the anion is being displaced. Hot in my apartment. Thought summer was over. So let's look at okay, we'll give you a moment to write that down. Okay, so let's put how many of each we have. Here I see 1 potassium, 1 bromine, and 2 fluorines. All right. Over here I have 1 potassium, 1 fluorine, and 2 bromines. All right. So let's see, the potassiums are already balanced. All right. So I can do either the fluorine or the bromine. All right. Well, here I have 2 fluorines, there I have 1. So I'm going to put a 2 there. So that's going to give me 1 potassium times 2 is 2 potassiums. 1 fluorine times 2 is 2 fluorines. Okay, 2 fluorines. So now I have, well, the potassiums are no longer balanced. Let's balance the potassiums now. Here I have 2 potassiums, here I have 1. So I'm going to put a 2 here to balance the potassium. 1 potassium times 2 is 2 potassiums. 1 bromine times 2 is 2 bromines. 2, 2, 2, 2, 2, 2. All right, and as always, we're going to go back and we're going to check. All right, 1 potassium times 2 is 2 potassiums. 1 potassium times 2 is 2 potassiums. 1 bromine times 2 is 2 bromines. 1 bromine times 2 is 2 bromines. 1 fluorine times 2 is 2 fluorines. 1 fluorine times 2 is 2 fluorines. We're done. We're done. So what kind of reaction is this? Is it single displacement? Come on, we should be able to do this a little faster. Is this single displacement? Or
Single
is it synthesis? Is it a synthesis reaction?
No.
No, it's not. Synthesis only has one product. This has two. Is it a decomposition reaction?
No, because it has an element for one of the reactants.
No, because it has two reactants. Decomposition only has one reactant. Decomposition only has one reactant. Is this an oxidation reduction? Come on, how do we spot oxidation reduction? It's got a
If it has a pure element.
It's got a pure element there and a pure element there. This is oxidation reduction, right? Notice here the fluorine is -1 and here the fluorine is neutral. Here the bromine is neutral, here the bromine is -1, right? So it is oxidation reduction. Now let's check and see if it's single displacement. Can I draw those little arcs? Sure I can. The fluorine and the bromine are trading places. The fluorine and the bromine are trading places. So here, it's the anion that's being displaced, not the cation. In the previous example, we saw the copper and the aluminum were trading places, right? The copper was displacing the aluminum. Here, the fluorine is displacing the bromine, right? So in the other one, it was the metal cation being substituted. Here, it's the anion that's being displaced, the anion, right? So what's the general format for this? It is single substitution, but our book only shows the cation being displaced. But here, I can have AX. Remember, we're going to use the lower letters in the alphabet for the metals and the letters at the end of the alphabet for the non-metals. This is going to be AX plus Y, gives me AY plus X. All right, AY plus X. And we can see here that X and Y trade places. X and Y trade places. X and Y trade places. Okay, any questions? Any questions? All right, let's look at another one. Oh, let's see here. No, let's do this. I don't know if you can read that. CA, here, let me write that a little clearer. Let me write that a little clearer. So here I have a polyatomic ion, polyatomic anion, nitrate anion. Okay. Now, watch what I'm going to do here. Okay, I'm going to balance the polyatomic ion. I see NO3 on both sides. It doesn't break up. So why make it more complicated? I'm just going to write NO3. It will balance NO3. I know I have NO3 on both sides. And copy on both sides. So you might say I'm balancing ions here rather than elements. Right? This is calcium cation, chloride anion, silver cation, nitrate anion. Okay. Everybody have that? Anybody still writing? Nobody ever answers. All right. So here I have 1 calcium, 2 chlorides, 1 silver. Now I cover up. I see 1 NO3. There's just 1 nitrate. Just 1 nitrate. Okay. Whoop. Now here I have 1 calcium. We're going to come back to this nitrate here. Here I see 1 silver and 1 chlorine. Okay. Now we haven't seen anything like. Actually, we have seen this. You did. You guys did representative nomenclature. Okay. You saw this. So here
Yes.
I'm going to cover up that subscript. All right. There's 1 nitrate anion times 2 is 2 nitrate anions. So what's immediately before the 2? A parenthesis. So that 2 is going to multiply whatever is inside the parenthesis. The 2 is going to multiply whatever is inside the parenthesis. What's inside the parenthesis? 1 nitrate anion. So multiplying times 2 is 2 nitrate anions. 2 nitrate anions. Okay? So let's see. The nitrates are not balanced and the chlorines are not balanced. All right, well, let's do the easy one first. Let's do the chlorines. All right, does everybody have this? Is everybody caught up?
Yes.
Okay.
Yes.
So here I have 2 chlorines, here I have 1. So I'm going to put a 2 here, a 2 there. All right, now 1 silver times 2 is 2 silvers. 1 chlorine times 2 is 2 chlorines. Okay. Now I'm going to shy away from those nitrates until I have to mess with them. All right? Because it's a polyatomic. I don't want to have to mess with polyatomics if I don't have to. All right, so the calciums are balanced, the chlorines are balanced, the silvers are not. The silvers are not balanced. Here I have 1 silver, there I have 2 silvers. So I can put a 2 here, a 2 there. You cover up, 1 silver times 2 is 2 silver. Now here, I'm going to cover up the silver. What's left is my polyatomic ion, NO3. I know it's polyatomic because there's 2 capital letters there. It must be polyatomic. There's 2 capital letters. So there's 1 nitrate anion, NO3. No parenthesis means there's just 1 copy of it. 1 nitrate times 2 is 2 nitrates. 1, 2, 2, 2, 1, 2, 2, 2. So I didn't have to mess with this parenthesis over here. Right? Did not have to mess with it. All right? Now, let's go back and check. 1 calcium, 1 calcium and 1 calcium. 1 times 2 is 2 chlorines. 2 times 1 is 2 chlorines. 1 silver times 2 is 2 silvers. 1 silver times 2 is 2 silvers. There's my 1 nitrate times 2 is 2 nitrates. Here I have a coefficient of 1. There's 1 nitrate. 1 nitrate times 2 is 2 nitrates. I'm balanced. I'm balanced. All right? So I can erase all this on the bottom and let's discuss what sort of reaction type this is. Can I erase this? Does anybody have any questions? Anybody have any questions? Sorry, go ahead.
No, go ahead and erase it.
You say don't erase it?
No, go ahead and erase it.
Go ahead and erase it. Now, if you wanted to, you could break this up and put nitrogen and oxygen instead of nitrate. You could do that. It's a lot easier not to break up the polyatomic ion, though. All right? Now, whew, man, it's hot. I'm going to faint. All right. So, is this a synthesis reaction?
No.
No, it's not. It's got two products. Can't be synthesis. Is it a decomposition reaction?
No.
No, it's not. It's got two reactants. Cannot be decomposition. Is it oxidation reduction?
No.
Why not?
Because there's no pure element on either
No
side.
pure element. There's a compound, a compound, a compound, a compound. Cannot be a oxidation reduction, at least by the definitions we're going by. Is it single substitution?
Yes.
No, it's not.
It's not?
Single substitution has to have a pure element in it,
Ah, shoot.
right? Single substitution looks like this. AX plus B gives me
Equal.
BX plus A. There's pure elements. There's pure elements. Or if I substitute the anion, AX plus Y gives me AY plus X. Pure elements. Pure elements. This is not single substitution. So does that mean it's just nothing? No. Obviously, I would not have picked something that's nothing. Pay attention here. This is what's called double displacement. Double displacement. Okay? Now, with double, notice here, both the cation and the anion have traded partners. Both the cation and the anion have traded partners. Here, the calcium is with the chlorine. Over here, the silver is with the chlorine. Here, the silver is with the nitrate. Here, the calcium is with the nitrate. Both of them have traded partners. Or we can look at it in a reverse manner from the anion point of view. The chlorine is with the calcium over here. Over here, the chlorine is with the silver. Over here, the nitrate is with the silver. Over here, the nitrate is with the calcium. Both the cation and the anion have traded partners. So how can I write a general format? AX, remember, the lower letters are the metals. The higher letters are in the alphabet are the anions. So AX plus BY gives me, need an arrow there, an arrow, gives me AY plus BX. Okay, it's a little different notation than our textbook has. I like this notation much better because, again, it lets you know the lower letters are the metal cations, the higher letters are the non-metal anions. And notice here, all right, so here the A is with the X. On the other side, the A is going to be with the Y. Over here, I draw the inner loop. The B should be with the X over there. There they are. The B is with the X. Okay? Here, I like to use an analogy for this. And if we were in the classroom quite often, I'll call up two gentlemen from the class and two ladies from the class. And I'll ask them to start dancing, right? Slow dancing, all right? And I think we've all seen these like dancing contests on TV or some show, some old movie or something. And the music stops or somebody claps their hands and what happens? You trade partners, right? So the lady goes from one guy to the other guy, or the guy goes from one lady to the other lady, all right? So that's what's happening here. Think of the metal cations as the guys and the non-metal anions as the ladies. The music stops, they trade partners. They trade partners. Okay? They're still dancing, but they trade partners. Right, so that's kind of what a double displacement reaction is. That's kind of what a double displacement reaction is. Okay? Any questions or comments here? Any questions or comments?
I've got nothing.
Nobody has any questions or comments. Now, are you ready to do an assignment on this? I don't think so. I tell you what, I can give you a couple, but I'm not going to collect them to practice. I'll give you the assignment next class, right? Next class, because we still have 2 more reaction types to do. We still have 2 more reaction types to do. I don't want to give you the assignment until that, okay? Actually, I'm going to stop recording here